machine.
So the next talk is by Daniel, and he will talk about our work of integrating effect handlers, algebraic effect handlers, into WebAssembly.
Yes, thank you. Am I audible?
Do you need that?
I think I have a mic here, but I don't know if this one is audible. It's audible? Okay, good. Thank you very much. My pleasure to be here. As Andreas said, I'm going to talk about sort of retrofitting effect handlers onto WebAssembly for the purpose of giving a way of doing stack switching inside core WASM. And this is joint work with a lot of people. And as you can see, this is like a pretty full slide already. But one thing I want to draw attention to is that if you think this work is interesting, and if you would like to work in this, I'm sure I can fit more pictures onto the slide. So just get in touch with me. And I'm interested in everything from like students to do research on this, also to engine implementers to prototyping this in their engines. So there's a little address down here. You can follow that. If you cannot remember this, it will also be on the last slide of this talk. Okay. With that in mind, let me dive straight in. So what is the motivation here? Well, the motivation is, if you look at all the program languages we have out there, very often you have some kind of non-local control flow feature in the language. And even some languages have the whole identity spun up on non-local control flow. So I made a list here. I've just sort of handpicked a few, and I hope you all agree with me. These are like real-world things you'll find in languages out there. I hope you also agree that the languages that are sort of listed here are all real-world or industrial-strength languages. So this is not something I'm just making up from my small research language. And in particular, I decided not to put any of my own languages here. But async await, for instance, is a thing that many people care about. And right now, it's not easy to express in WASM if you want to compile that. And same with coroutines and generators lightweight threads and so forth. So the question is really, how do I compile this? And the answer is, you can't. Asterisk. And then there's some subject to term and conditions. And those are, of course, is possible, but it's not possible in core WASM itself. So what could we do to address this? Well, we could add each abstraction as a primitive to WASM. And then, the next 700 of these will come around. We add 700 different instruction sets to WASM. It's not really going to scale. So let's just forget about that idea immediately. What you can do, though, and you can do this today, is that you can do a source-to-source transformation, which basically is akin to doing a CPS transform over your source program. And that's what people do today with a thing called asyncify. So let's look a little bit at what asyncify is doing. So here's a little program. It's a do something. It calls a function called bar first with an argument arg, and then whatever that returns, it plumps that into foo. This might look simple on the surface, but I can guarantee you this program is nothing but, it's not very simple at all when you look through the lens of asyncify. Because you have to ask a question here. What can bar do? Can bar suspend execution? Okay, because that's going to have a sort of a ripple up effect, a bubble up effect on how this code is going to be compiled. And similarly, you have to ask, can foo do the same? And okay, so basically when you compile this with asyncify, this is sort of the result you get. Okay, so those lines of code expands into this kind of thing here. And I should say here, disclaimer, this is not exactly the code asyncify gives you, but I've sort of fitted it for the slide here. But it's in essence what's going on. So I don't expect you to read this code. It's just to show you what's going on. But I will highlight a few sections here. So the first thing you'll see in your function, you have like a prelude in all your functions. That's basically to test, am I in a state where I'm restoring, or am I in the state where I'm calling this function for the first time? And once you've done that, then you actually have to walk your way down through all these branches to say, okay, now I need to either call it or restore my context. And then once you're done, you have to check, am I actually suspending, unwinding the stack, or am I done computing? So you have these phases in your function now. Right, so let's try to characterize a little bit. So I sort of divide up to three pros and cons here. I would say one pro is it is expressive. I would hypothesize you can probably do all the applications that I listed before, the features that I listed before. It's a source-to-source transformation, so it works today, and it's heavily optimizable under closed-world assumptions. So that means you can actually get rid of many of the branches that are showed. Sort of a con is that in the general case, you cannot actually get rid of all the branches. So you are going to have some kind of code blow up, and your sort of pure line, straight line code, if it has a function call inside it, then it's no longer straight line. It will have branches inserted to deal with this unwinding and rewinding. And it's sort of inherently a whole program approach, which is unfortunate if you're interested in separate compilation and stuff like that. Okay, so what are the sort of key primitives that we have in Asyncify? Well, they are called unwind stack, delimit unwind. So that's saying unwind up to here, and then you have rewind stack, which reinstalls the thing you have captured, or goes back to where you were before. And if you look at this, and if you're me and you look at this looks really familiar. So we could do we could sort of rename these terms a bit, and we could say, what if we call them like suspend continuation, and we call them delimit suspend, so suspend up to here, and then resume continuation. Then basically what we're looking at is just a particular implementation of what is known as delimited continuations in the literature. And I would say that's exactly what Asyncify gives us, more or less. It's delimited continuations over unit to unit, which is insufficient to implement many of the things we care about. And the way to look at this sort of intervention is that you see continuation as sort of a handle to an execution stack, to a particular stack. You get to view it through continuation. Whatever remains to be done on that execution stack, that's your continuation. That's the way to think about the relationship between stacks and continuations. Right. So what is the solution? Well, why don't we just take whatever Asyncify is doing, this idea of delimited continuation, and we turn it into a bespoke instruction set? Very good idea. But now, where do you start? Because if you open the literature, you'll find that a lot of work has been put into this kind of work before. The earliest one I put here is Verleisen, but it actually goes before that with Core CC and others. So which one do we pick? And the one we picked is, well, no surprise from the title, is the latest one based on plug and pattern as effect handlers. And maybe just justify that choice quickly, is that you can basically see effect handlers as a structured form, a structured interface for programming with non-local control flow. And given that control flow is already structured in WebAssembly, we've already seen maybe there's some synergy here. And the way I think Andrew Rao put this best, and he said this many times over the years, is that effect handlers are basically to limit continuation what while is to go to. And I think that's a very good way to conceptually think about it. But more than that, I think where effect handlers excel over the others is that actually it's very compatible with the simple types of WebAssembly. And in particular, it synergizes really well with the stack typing. We don't need to do any changes to how the type system works, which is not true for many of the others. They have a very complicated typing schemes, mostly. It's also an imperative control structure, unlike many of the others. You can make the others into imperative control structures, but it will require some changes. So basically, effect handlers are like exception handlers, if you like. Predictable performance, I think more or less all of them have that, but you get that here too. And it also works with and without garbage collection, which is a plus. I put here in parentheses one-shot continuation. So I think this thing here is only true if you have one-shot continuation. If you have multi-shot continuations, then you can form cycles, and then you probably need full-blown garbage collection to clean it up. So what we restrict ourselves to here is one-shot continuations. And that another reason for that is also it works really well with what's already in WASM, and the assumption that WASM makes, basically it's a linear world. So being able to only enter a context once is basically what many systems would expect. Once you can do it multiple times, then funny things can happen if you do not expect it. Okay, so this is my favorite slide of the talk here, because this is the entire instruction set of what we call WasmFX, the extension to WASM with effect handlers. So there is one new type. That's a continuation type. This is your type of a stack, if you like. This is the one that gives you a view over the stack, and it's parameterized by a stack type. So for those who don't know, well, stack type, function type is basically the same in WASM, but the way this says here, like, I expect some sigmas to be on my stack, and these are exactly the arguments that I need to run. To start me, you need to supply these sigmas, and when I'm done, I'm going to return you these taus on the stack. That's what you get back. Okay. And then the next extension, which is not really an extension, is the tag here, which we call a control tag. The reason I say it's not really an extension is that they actually come in with the exception handling proposal. So the only thing we add is this result thing. So now, instead of only being able to throw them up in a context and never come back, now you can actually come back from throwing these. So basically this says here, like, a tag is a thing that carries some payload sigmas and returns you some taus. In the literature, this is what you usually call a control verifier. This is what we're going for here. So this is your shift, if you're familiar with shift reset, or this is your control prompt. And then we have 3 core. Sorry, yeah.
Looks a lot like a function type. How does it differ from?
Well, it is basically a function type in the sense that I have. It has the same type as this up here, right? It's the same stack type. It is saying, like, in order to invoke me, you need to supply me with the sigmas, like the arguments to a function. It's the same thing. And when I come back, I'm giving you back all these taus. So it is a function in that sense type.
You're clever guys. You wouldn't have introduced a new type of function types would do.
I have not introduced this type. This is something that's already in WASM.
Clever guys too. So there must be some difference here. I don't understand.
Well,
Phil, are you asking about the tag or the continuation type?
I'm asking about the tag.
Okay, just to clarify.
right, okay. So the question is this just a function type?
My understanding.
Andreas can correct me if I'm wrong. My understanding within WASM, the way a continuation type would be expressed is it actually is a function type underneath, right? So the WebAssembly modules has a list of function types. The way you express a continuation tag is it's continuation indexed to one of these function types that have already been declared. So we're not creating a new way to express function types, just a different place you can reference them. Does that answer your question, Phil?
Not really.
So he's just putting up syntax here. Really,
Yeah.
param result is a function type.
It is a function
But
type.
the tag is a runtime value that is associated with this function type, right? Like,
Yeah.
So functions are fixed statically, whereas tags might be dynamic.
No, tags are also statically fixed.
no, but
I just wanted the intuition about what the difference is.
it's like
Maybe you should just go on.
Yeah.
About how this is.
like an exception identifier, right?
Yeah.
A tag is like an exception identifier. So it is a name you can raise and catch somewhere,
Yes.
which identifies a certain effect. And there is then a continuation with a certain function type attached to it, but that is a separate kind of thing in terms of semantics.
Yeah. Ben?
Just put it
Yeah.
this way, there's a pattern match built in.
There's a pattern match built into resume. This one here, yeah, I'm getting to that. Yes. It is. We're using the function types here, but in a technical sense, and this is not really an important point, it is a different space we are operating in. It's not the function space, but we're just using the same syntax. And it's the same way you declare them, and it's just an index into.
These are a special subset of the functions that we can
Yeah, but they're already in WASM today. It's not a thing we add with this, but in a technical sense, they are actually different. But in WASM, they are just all conflated into to the function space and using the same syntax.
I think once you explain resume, that becomes clear how they.
Okay, we try. Yes, we move on. But 3 core instructions. The first one is continue. It's a way to create a new continuation. So you give it a function, and then it will create a new execution stack for you, where that function is ready to run. Then you have suspend, and it's parameterized by a tag. One of these up here is saying, I want to suspend execution of this stack, and the sort of signal I'm giving is this tag here. If you think of in terms of exceptions, it's this exception that I'm throwing, this tag. Okay. Then you have resume. That's the one that starts or continues a continuation. So it does both. It's the one you invoke initially to start a continuation, but also if you get back a suspended continuation, you use this. And it has, as Ben was saying, like it pattern matches on tags. And what it does here, this is the name of a tag, so this one up here. It maps that to like a label that's in scope of the resume. And I'll make that very concrete in the next slide when I'll give you an example. But that's basically how you implement the cases. So you can pattern match on the different tags by saying, well, if this tag is raised, then jump to this label in my ambient context. So it's a jump table, basically. Okay, so those are the core instructions. I also just want to say briefly that there are 3 other instructions, but they're not necessary, actually. You can get around without these. One is cont bind. That's partial application for continuations. I'll get it back to later why that could be useful. And then we have sort of a thing just like resume, but resume throw, that injects an exception into the continuation. That's useful for cancellation if you want to clean up. But you technically don't need any of this. And then barrier is a thing to say no control shall pass through here. So this gives you sort of a catch-all handle around your context.
But technically don't need. Those 3 can be expressed between.
Yes, so if you're a compiler, you can get around this bit code by duplicating the code you're generating. This one here, you can get around by having a special value fit into your resume. So you define your own API, and then you can do that. So you technically don't need them. But given that exceptions are already coming in, it seems kind of natural to use them. So to do the cleanup and give a way to do that. But if you don't want to use it, you can also get around without it.
And then Cognu, you said takes the function, but you didn't give the function as a parameter.
No, but that will come. It'll be on the stack. I'm not giving you the types yet. I'll get to that, but that's a very good point. Yeah. So just the status of where we are with this proposal and this work. All of it has a formal specification now, and all of it has an implementation, a reference implementation that we have built on top of the WASM reference interpreter. And then most of them have an implementation in WASM time. That's what we're currently working on. And you'll see two of them that don't have is resume throw and barrier. And resume throw is not there because there's no exception support yet in WASM time. It's not landed yet, so we're waiting on that to land before we can implement it. And then barrier is just out of laziness. Don't really have any, not really been really keen to do this. Maybe one day it will be there. All right. So let me give the example. Let's make the instruction set concrete here. Let's try to do some yield style generators. So first, what I do is I declare a tag. I call it gen. It's parameterized by an integer. The result type is implicit here. This is just syntactic sugar. Maybe I should have written it out, but it's basically unit when you don't write it. Okay. And then I have a function called nats. So what do I do first? I declare a local called I, and it's by WebAssembly semantics serial initialized, so I don't need to say that explicitly. And then I start a loop, which I give a label called produce next. Okay, I'll get back to that in a moment, what we use that for. The first thing we do is we suspend inside that loop with the value of I. So that's immediately going to suspend execution and transfer control upwards in our execution context. Then when we come back from that suspend, then we update or increment I by 1. That's what this slot is doing here. And then the next thing we do after that is we then branch to produce next. So that's basically saying do this loop one more time. So in WebAssembly semantics, the way you do a loop is you have to explicitly say you branch to that loop. If you don't, then you fall out. Okay. So that might seem a little bit odd, but that's how it is. Okay. Then let's define a sort of so that's our generator. Now let's define something that uses the generator. I call this sum, and I take as input some the number of iterations we run, and then an initial continuation that we're going to run. And then the first thing I have is I have some setup where I need to set up what is the current value we have and what is the state of our accumulator. And then I set up this handling loop. So you see here I have a loop that says consume next. And then inside this loop here I define a block called onGen, which when it's done, it will have an I32 on its stack, on the stack, and it will have a continuation on the stack. Okay. And then inside that block, that's when I actually run the resume. And what do I say in the resume here? I say, well, if the gen tag happens, then jump to the onGen in the context then. OnGen is in the context, it's just above it. Okay, and then I run with the current value of k, the current continuation that I have. And then I print the result. Oh, that's a missing thing. There should be a return here also. But yeah, okay. Then if or maybe I should say this first actually. So the only point where this print executes is when I return successfully from resume. So if I don't suspend, that's when I flow down into here. Okay. But if there is a suspend, then I flow to I branch to the onGen, and now we need to know something else about branching in WebAssembly is that when you branch to a block, you branch to after it, not to the beginning of it like you did with a loop. So that's a bit different. That's the semantics. So if I'm suspending with the tag gen, I'm going to jump to this code of block here, and in here I set up the next continuation because that's on the stack. That's what it says here, and I set up the next save the current value we have. That's the I32 that I got, and then I increment my sum, and then I say down here I say, well, I branch to the next consume, so I continue the loop if I still have more things to run, or if I want to get more values, and then finally if this doesn't run, then I flow through here and I print the value. Okay. So if you write this expression here, call sum of I32 const 10, so that means I'm calling sum here with 10, and oh, there's a typo there too, it should not be a bracket there. Then I give the initial continuation to be the function nats, is the one over there. Then it returns 55. I don't know, I don't know, maybe you don't believe a slide. I could run it for you here, and we can just see it with our own eyes. So I have the reference implementation here. So WasmFX, I think it's called generator, and then I think I just call the program main. Oh, we should see the same output here. Let's pray. Ooh, yes, so we get a 55 out. Okay. So that's basically that's how we could do a yield start generator. It's one way. You can do it in other ways also, but this is one way you could do it, and it fits on a slide. So that's why it's nice. So to address Phil's question about the types, let's move a little bit on and look a little deeper at what the instruction set looks like. So as I mentioned, there is a new reference type called cont, which is parameterized by the function type or stack type. And then we have the instruction cont new, and here's the type of cont new. It says I should have like a reference to a function that expects some sigmas and returns some taus. And then what I give you back, I give you a reference to a continuation that has exactly that function type inside it. Okay, but it's suspended. I don't run the continuation. You get like a sleeping thing back, and you have to explicitly run it in order to execute it. Okay. Then we can suspend continuations. This is really simple. It says like if you suspend the tag, then you better have some sigmas on the stack, and then I give you back some taus. Where are these sigmas coming from? Well, it's exactly what the tag expects. Okay, and the return type is exactly what the tag tells you it will return with. So that's nothing really fancy going on there. This one here, resume, is the more interesting one. Okay, so if you sort of ignore the tag list for now, you can see I put like a little white space here, so maybe you can imagine what's going to appear in a moment. But if you just look at resume, then basically what I'm saying here is that there better be some sigmas on the stack, and those sigmas should be the same as what the continuation that's on the stack expects. Okay, and that continuation is going to return a tau, which is going to be the ultimate return type of resume also. So once the continuation is run to completion, I'm going to return via the resume. I'm just going to bubble that value that I got out. Okay. Where it's interesting is when you add the sort of a filter list here with the tags and handler labels. So this says here, like, I have a mapping from tag to H, to the label H. Then it better be the case that my tag will expect have some payload sigma i's. It better be the case that in the block where I handle tag, I should expect to have exactly the same sigma i's on the stack. Okay, but I should also expect to have a new continuation, the way I can resume or go back to where I suspended. And here I say, well, it better be the case that my continuation takes whatever my operation or my tag expected as output. So the return type of the tag becomes the input type of the continuation. But still, the ultimate return type of the continuation is the same as what I expected in the context is tau. Okay, so that's really all that's going on. It's just making all the types line up.
How does the sigma star there relate to the sigma sub I star and alpha star?
Good question. They don't relate at all because these sigma i's here are coming from the tags. They're coming from the context you are running in. So this is the payload you suspend with. Okay, the resumes up here, these two here, these are like when you apply the continuation. So if you're inside the block H, then HI, then what you'll be continuing with would be the tau i's you apply here instead. That's what will happen. But these sigmas here are not related to these sigmas here in
I see that tag is about what happens if you raise
exactly.
tag while
Exactly.
executing that
Yep,
continuation.
that's right. So the tag is exactly telling you what's going to happen when you suspend the execution context. You move up to the ambient context, and then yeah, absolutely. Okay, let's do one more example. So let's do lightweight threads. So they might look like this. We have a type, a task C, so the continuation task. It's a continuation from unit to unit, and then I have a tag yield for suspending execution. It's also unit to unit. And then I have an interesting tag here called spawn, which is parameterized by a continuation task. So it takes a reference to a continuation as input. And then I have a definition of a task here. It's just taking some ID as input, and then it's printing its ID, and then it's suspending, and then it's printing its ID. Okay. So here's what the scheduler for this would look like. So first, again, as we had before with the generator, we have some local setup. What I'm setting up here is I'm just declaring some local variables to handle the next continuation to run, or next thread, if you like, in this, or task in this analogy. And then I have this whole scheduler loop here, which is really interesting. So, like before in the generator, I had a loop to sort of keep looping around and handling the next continuation. This is the same thing that's happening here. But now you'll see I've layered two blocks on top of each other. I have onSpawn and onYield because I have two tags I can handle now. And then inside the onYield, that's when I actually do the resume. I'm saying here, if spawn happens, then jump to onSpawn. If yield happens, then jump to onYield. And just get the next continuation and run it. Then if we are done, we need to check if the queue we have is empty. So I'm assuming a queue somewhere. If it's not empty, then we can just we just dequeue the next continuation from there, and then we branch to the schedule next, which is going all the way up here and then running the resume one more time. If yield happens, then we fall through to, have I animated this? I think I have. Oh, wow. Then we fall through to this block here. We jump to this block here, where we first enqueue the continuation that's on the stack. Then we dequeue from the continuation queue, and then we schedule again. We jump back. Okay. Same with onSpawn. We have a we have actually two continuations here. We have the payload we got, and then we have the continuation arising from the suspend itself. So here we set one, and we enqueue one, and then we branch to schedule next, and we run around again. Okay, so that's how we could do a scheduler. And this is called BFS because it's going to actually schedule your tree and breadth first way, if you look at our concurrency graph. All right, so here's how we might glue it together. You have a main task. It's going to spawn 4 tasks, but there's a slight problem here. It doesn't type check. Why doesn't it type check? Well, if you look at the type of task, it expects an ID as input, but I have given no ID here. Like my task C here is of unit to unit. So it's not good. So what can we do about this? Well, one thing we could do is I could sort of thread the parameter around. That would be one way to do it. But I've just written all this code, and it kind of sucks to have to rewrite this. So can I do something else? Yes, I can do something else. And this is where compbind comes in. So compbind allows me to partially apply a continuation. And it has this signature here. It's parameterized by 2 continuation types. CT is the source type. That's what I'm given. And CT prime is the type that I'm transforming my continuation into. Okay. So I'll have some sigma zeros on the stack. I consume those, and I give you, and I have a continuation reference of type CT. Then I give you back a continuation of type CT prime. So I try to line things up here to show you. CT has this type here, and then CT prime is the same as CT, except I have consumed the prefix. Okay. So this is a way to sort of change the type of a continuation, but it doesn't run the continuation. It just sort of pushes the arguments down to it. Okay, with that in mind, you can write code like this instead for the main task. So you see here I've introduced a new type alias also for an I task from like I32 to unit, and now I'm going to transform an I task into a task, and I'm going to give them IDs, initial argument 0, 1, 2, and 3. Okay, and if you run this, it should print this sequence here. So that will tell you that they're not all run in straight line sequence. So let's just try to run this also. I think I call this LWT. Boop, yes. And that should be the sequence you see 0, 1, 2, 3, 0, 1, 2, 3. So there's been some interleaving in between. If there were no interleaving, you will have seen 0, 0, 1, 1, 2, 2, and so forth. Okay, almost at the end here now. So one thing that we often don't talk about with this, but I think is a really key feature of it, is that it allows you to do modular composition. So now we have 2 things we have defined so far in the talk. We have a generator, and we have a lightweight threading scheduler. Okay. So one way we could compose them is what I try to draw in this picture here. Is we could have like our scheduler lightweight threading at the outermost level. and then inside that I could run my 4 threads, and each of those 4 threads could run a generator. Okay, if I do that, then it will print the sequence 55, 55, 55. So I think I have that. Now we need multiple modules because I'm using previous code, and then we need LWT gen, this one here. And I think I called this compose LWT gen. Yes. Okay. So here each strand, each thread has run a generator, and the gen effect control tags that's happened has been handled by each local gen handler, and the yields and spawns have been handled by the outermost scheduler. Okay, but that's another way we could layer this. We could do this instead. We could have the generator at the outermost level, and then have the scheduler inside that. What does that mean? That means now each of these threads here contribute to the generator, to what we're going to sum up. Okay, so it gives us a different semantics. The only thing I changed here is the order in which I call things. I have not changed like the logic in the code. And if you do this, so this is compose gen LWT. Now I get another number out, and I get only a single number now because now only the generator is only invoked once, and it's the one that's printing, and it will give me a 190 now. So yes. So that's another way. So that gives you modular composition, which I think is a key thing that it's very hard to achieve with many of the others I talked about earlier. Right. Last instruction I'll talk about is resume throw. So it's basically like with resume, except that we now have an exception tag that we inject into the context. And otherwise this is the same. And we have some kind of payload to the exception tag. With this you could do something like this. I think maybe you could do thread cancellation. So if you just want to get the first thread that finishes, then you might want to clean up all the other ones if they had some resources or stuff they were closing over. In our example here, there's none, but we can imagine there are some. Then this is what you'll insert in the scheduler loop. So when you're done, you enter this cleanup loop instead, and then you do a try catch, and then you resume throw inside there. So you are called the exception cancel, and it will inject the cancel into the continuation, and then they can run that and clean up. Technically, if I wanted to be really safe here, I would need to add some tag list here to bind the yield and the spawn also, because locally the continuation could handle the cancellation by spawning a new thread, if you like. But you can do that. And also, I'm sorry, Ben. People will know, and some people will not know, this is really old exception handling syntax in WASM. It's not what it looked like today, but this is the state the reference interpreter, and we have not updated for a while with the exception stuff. But yeah, so there'll be some minor syntactic changes to that, but that's what it is. Then what you can do is, if you take the example from before where we composed the library threads with the generators in each strand, then you'll find that instead of 55, 55, let me see here, I need to use the one that has the exception in it, and then I need to revert this order here. Then only one strand gets to complete, so we only see 55 printed out once. The other ones have been killed. Right. Okay, so very last thing I want to talk about is what is the power of this thing? And here is sort of an attempt at sort of trying to characterize it a bit abstractly, so looking at some reduction relations here for control. So I have here changed the syntax a little bit. I have a suspend that's parameterized by continuation, and then it will continue with the term m. And then my resume is now taking one of these cont objects, which is subscript by the context that's been captured. That's the notation I'm using here. And it doesn't really matter if this is called by value or called by name. This is called by name I've used, but it's just because it lets me write less. But it doesn't really matter, and we don't need that for this discussion. So that basically what I'm going to do now is I'm going to say, okay, if you're going to look at what can we encode for this thing, we could look at how do we interact with the context. Okay, that's two things we could do, at either the suspend or the resume, and it leads to 4 different options. The first thing we can do is that when we suspend, so this is what I call abortive capture. When we capture the continuation, we could erase the current context we're in. That's what this line here is doing. You say here, I suspended the context E, then I'm just going to continue as M in a blank context, okay, with the continuation, with the context I've captured. And then when I resume, I'm resuming some context E, then what I'm going to do is I'm going to erase that context, and then I'm going to install the E prime that I had captured on continuous with M. This gives you some semantics that's kind of similar to what threads are doing. Is what I like to call double abortive. So you abort context both when you suspend and when you resume. Another thing you could do is that you could abort when you suspend. So this is what's happening here. We are in some context E. We capture that E as a continuation, but we run M in a blank context. But what we could then do we could be composable when we resume. So instead of aborting the context we're in, the E here, we now splice the captured continuation with the current continuation of the current context. Okay, that's what's happening here. And this semantics here, this is what effect handler, shift reset, control prompt, all of them I showed earlier, I think, they do. This is the characteristic reduction for those. Then you could also do this thing here. You could have composable capture. So beforehand we were aborting the context, but we could actually also leave the context in place. And that's what I'm doing here. So I suspend in some E, but I leave the E in place. And then I verify the context and give you a continuation to that context. And then we could compose when we resume also like we did before. Okay. Then the final option. Oh yeah, I should say, this is like what in Racket, what call with the composable continuation do. This is exactly the equations for that. Then the last thing we could do is we could say we do composable capture and abortive resume. So it means like when I capture the continuation with my suspend, I leave it in place, but when I resume, I erase the current E and install the E prime that I had captured. And this is what callcc does. Okay. So there's something funny going on here. I want to draw your attention to. Don't know if it renders here, but I've highlighted these in red here. And you'll see up here. So this E here appears twice on the right-hand side. It's a bit weird. And also down here. So when I capture the continuation, I have a copy to the context that I'm running in. That's basically what this says. And that's not the case up here. And it turns out that I think this is where a lot of the wacky behavior for callcc comes from. Because what you can do if you have this is you can actually, from one-shot continuations, encode multi-shot continuations. So you can get multi-shot continuations for free here. Why? Because the semantics is already giving you that. I've not said anything about the shotness and one-shotness and multi-shotness of these operators here. But there's a paper from Popple 85 that shows how to do this by Freeman and Haynes. It's called Constraining Control, where they suggest that you argue for that. Let's just have callcc1, where you can only invoke the continuation once, because hey, it's enough, and they then give a construction for how we can construct callcc from callcc1. But that means when you do this, what you lead in through the back door is also you get all the wacky behaviors with multi-shot continuations and linear resources, even though you only have one-shot continuations. Okay. It also means something else. It means that the effect handlers and shift reset and whatever we choose as a basis and what we're running with cannot encode these because there's no way to simulate an extra copy of the context up here. Likewise, callcc if it can simulate effect handler shift reset, but only if you have state in the language, which WASM has. So this will be able to simulate this up here. Okay, so we in some dimensions we're less expressive than callcc, in other dimensions we're more expressive if you remove some of the language. Yes, Phil?
So you've given us 4 semantics.
Yes.
Presumably you pick one of these.
Yes.
And I guess what you've done is picking the one which you let the other 3 in terms.
No. It's purposely not for that, because of the reason I'm saying down here. If you pick the 2 of the latter ones here, now you can get multi-shot continuations from single-shot continuations, and that can lead to. No, we don't want that. We want to keep the linear view of the world. Right, it's number 2. This is the effect handlers one. This is the one we run with.
The most powerful one that remains single shot.
Yes, and with this one here, you get. You can, this is the thing that any paper you read after the 80s will have done. Okay, so this is what I think people agree on. This is sane semantics. This one up here is interesting. This is basically if you read a paper from Verleisen, also Verleisen C basically has this semantics. Okay, but we want to avoid this situation here where you inadvertently can copy your context. And it sort of also sheds a little bit of light on the power of callcc, I think, and I think this is only known as folklore in the literature. I don't think this is widely known. You can look at this paper. There's no proof of the construction, but I think I have a proof of it. But I conjecture for now. But yeah, yes, Sam.
Probably worth looking at that if you did have multi-shot continuous back.
worth pointing out that if you do have multi-shot continuations, then the second one is able to express everything.
Exactly. That was a question from the back also? No? Sorry. Yes. Okay. I'll do that.
You got mine.
Yeah, got yours, yeah.
Just a quick question about the last construction. Do they somehow have to reify the stacks on their own? Because don't multi-shot continuations require copying stacks?
Yes, they do. But in order to implement core CC, you need to copy the stack already. This is the insight, I think. This is where I get it from. Yes, but when I saw this first time, and I was a PhD student writing up my PhD dissertation, I was like, oh, this was mind-bending. But I was like, I'm writing up, I better stash it to the side and not look too deep at it. And then I went back last year to look at it, and yeah, it is it's kind of interesting. But it's kind of clear, once you understand the construction they give, it's quite easy to see why it works. Okay, but as Sam said, if you have multi-shot continuations, you could do all of them. And that's one of the extensions we could do. And we have a conclone extension that take a continuation and give you back two copies of it. Another thing we could maybe do is that our resume blocks are unnamed. By that I mean, like, there's no way to refer to the exact resume you want to hit in your ambient stack. We could do that. We could give a name to them and then pass that name down. And then what you'll do is you say, I want to suspend to this particular handler. Then you go to some particular place in your ambient context. That'll be one way. And that gives you some kind of generativity also now, which we don't have with our approach. If you wanted that generativity, we could also do first-class tags. And by that I mean, like, we could give some way of generating them dynamically, and then match them dynamically, and then be able to pass them around like tags. And this is actually, if you know OCaml, that's what they do in the OCaml implementation of effect handlers. But we could do that. And with that, I want to finish and leave you with this resource list. And here is the link again. And if you're interested in any of this, please find me, and I will be happy to talk with you about opportunities and things here. Thank you.
Yeah, we already start running into the break again, but I think we can extend a little bit for more questions.
Thanks for a nice talk, Daniel. You began motivating this by showing Asyncify, the current state of the art.
Yeah.
And you said, oh, look, it gives you this really long thing.
Yeah.
So have you rewritten a version of Asyncify where the target is your new language set, and is it suitably smaller?
Yes and no. I've not rewritten Asyncify. It is on the to-do list to do. It's just it's a lot of engineering work. What we have done, though, is we have done experiments where we have, in C, we have defined like a fiber interface, so you can spawn different stacks. One is backed by the WasmFX instruction set, another one is backed by Asyncify. And there is a massive code size difference in that. So yes, we shrink quite a lot, and that's also unsurprising given that we add primitives that are not there before. But yes, so we've done that experiment. It's on the to-do list to do the thing you suggest by actually taking Asyncify and then swapping our instruction set instead. Yeah.
I mean, it's even worse, right? Because your function didn't even have any control flow, right? All this blow up is on every level of control flow, right? Every basic block basically has to do all this mess,
Yeah.
So I didn't implement this yet. It's on the top of my stack to implement. But one thing that concerns me, since we don't have linear types, is that you create a continuation. We have a little tiny garbage object.
Yeah.
I can see implementation-wise, it's actually easy to reuse this continuation object.
Yes.
It's the same type. But that requires another resume instruction. Have you thought about that?
Another resume instruction. It requires you to be able to tell what state you're in.
Suspend instruction, sorry.
Suspend instruction. No, I don't think it requires another suspend instruction. You can do this entirely in the engine. This is at least what we're doing. So in our implementation, we reuse the stack underneath. We don't actually create a new continuation every time. What we do create is that we bump a counter to tell whether or not what version of the continuation are you in. So when you actually invoke a continuation, we're going to compare two numbers and check if they are.
Yeah, I'm aware of that one. The stack resource is separate in mind. There's a continuation object, which is a small thing, and the stack is the big thing. And you can actually reuse the little continuation object too.
Yes, with a fat pointer.
But without using a fat pointer.
All right, okay, then I'll be happy to talk to you. We are using a fat pointer, yeah, okay. Yeah. Well.
Hi, so I think one thing that the Asyncify approach could give you, I haven't tried it, so I'm not sure, but I think it could give you a way of being safe in the face of Stack Overflow. You keep a counter on the depth of your call stack, and when it reaches a certain value, you stop here, and go all the way back to unwind the stack, and so you can have a handler for catching this kind of
to catch those stack overflows.
Yeah, and so you could avoid it, right? So you could make your language Stack Overflow safe, right?
I suppose that is possible, yeah.
So could you do something like that here? Or it's not possible at all?
It's not something I thought about in the source language at all. It's something I thought about in the target language. And there we do have checks to check that we don't overflow the stack. And if we do, we either crash or we expand the stack. Yeah, but I've not thought about it in the terms of can I do this in my source language?
I see.
Yeah.
So can I compile a language to WebAssembly using WasmFX in a way that doesn't have Stack Overflows? Can you have like segmented stacks or something?
Yeah. So that basically that's what we have in the implementation. We do segmented stacks. In
you have this?
Yeah.
Oh, okay.
That's what we do in the WasmTime implementation. Yes, that's exactly what we do.
So this is something specific to your project, or is something about WASM in general?
All right, that's specific to this project, but not really, because WasmTime already had it. We just reused the.
Can you remind me what WasmTime is?
WasmTime is an engine for Wasm developed by the Bytecode Alliance.
Oh, okay.
Yeah, it's a production-grade engine.
Okay.
Yeah.
But if I run this in the browser, then it won't actually be able to...
I don't think WasmTime will run in the browser.
No, but do you think eventually browsers will have Stack Overflow safety?
Yeah, I think so, yeah. I think, like, I hope V8 will pick some of this up.
Already implemented in V8.
Oh, okay.
For the JSPI.
Yeah.
Cool. Very nice. Thanks.
Yeah, so Sam said that this has already been implemented in V8 for the JS promise integration. Yeah, thank you. There's always some form of stack switching in there, but they do not have an implementation of this instruction set yet. I hope we can figure something out in the future. Yes.
Okay. I think we should leave people into
Yes.
a break.
Thank you.
Thank you again. Jenna.